All right, so welcome to pre-calculus, and this is just going to be chapter one, which is nothing more than just a review of everything that you've learned up until this point. I'm going to separate this into two parts, part one and part two. Part one covers just the beginning stuff like, section two, which is exponents and radicals. So I think let's just start there for now, okay? So when we think about exponents, we should be thinking about the exponent property or the definition, which is a to the n equals a times a times a, and we'll call that n times. All right, so that's our basic definition of an exponent. And then we learned basically 6 rules. So let's go ahead, let's outline them. So we have the power rule. And this one just says that if you have two different factors being multiplied and the bases are the same, all you do is add the exponents together. Then you have the, this is the product rule. Look at me already starting off incorrectly. So the product rule, the power rule, is when you have an exponent that is raised to another exponent. That's when you just multiply the exponents, okay? Then we have the opposite of the product rule, which would be the quotient rule. And if you think about the product rule, you add the exponents. Well, with the quotient rule, you do the exact opposite, so we are going to subtract the exponents. Okay? Then we have the zero exponent rule. And the zero exponent rule says that almost anything to the zero power is equal to 1, except a is not allowed to equal 0. 0 to the 0 is undefined. Okay? So let's see here. We have the product, power, quotient, zero exponent rule. We have the negative exponent rule. And sometimes people refer to this as the reciprocal rule because this says that if you have a base raised to a negative exponent, you can rewrite it as the reciprocal and make that exponent positive. And then the final rule, which is kind of like a general, we'll call it a general power or quotient rule, which looks something like this. And I'll do one of each. So let's say you have more than one factor inside a set of parentheses, and they have exponents, and they're all being raised to another exponent. Well, what you're allowed to do then is you can bring that exponent inside just by multiplying them together. And then the same thing also applies if you have a quotient. You could just go ahead and bring that power inside as well. Okay? So let me zoom out here just to summarize real quick. We have a product rule, power rule, quotient rule, zero exponent rule, negative exponent rule, and then a general case of the power and product, or the power and quotient. So let me show you how these work in a couple examples. Nothing too crazy. All right, so here's our first example here. We have z to the second times z to the fourth all over z to the third, z to the negative 1. Now, there is no, this is the way you do these problems every single time. Basically, if you could see a rule, just go ahead, stick with it, and do it, okay? So, for example here, even though I can see z's in the numerator and denominator, what I'm going to do is I'm just going to simplify the numerator as much as I can. So, I'm going to use my product rule and get z to the sixth. I'll do the same in the denominator. I get z to the second, because 3 plus negative 1 is 2. And now I can go ahead and apply my quotient rule to go ahead and give me z to the fourth. Now, let's look at another one. So let's see here. We got y to the negative 3, z to the negative 3, all over y to the negative 1. And we'll raise this entire thing to the negative 5. Okay? Once again, if you can see a move and you want to make that move, that's fine with me. If not, why don't we just go ahead and do something else? So, I can see right here, highlighted in blue, I can use the quotient rule if I really wanted to. But if I just kind of slow myself down and look, I notice that I have a negative exponent on the outside. Okay, so I got this negative exponent on the outside, and all of these exponents are negative as well. So what I'm going to do is I'm going to use that general quotient and product rule. So I'm going to get y to the 15th, z to the 15th, and then y to the 5th. And now from here, I can go ahead and subtract using my quotient rule to give us y to the 10th and z to the 15th. Okay? So let's go ahead. We'll do two more. So let's see here. Ooh, I like this one. Let's go ahead. We're going to do s to the second, t to the negative 4th, all over 5, s to the negative 1, t, all raised to the negative 2. Okay? So once again, why don't we just keep it simple? We're going to go ahead and use that general power rule. So this is going to give me s to the negative 4, t to the positive 8, 5 to the negative 2, s to the second, and t to the negative 2. Okay? So from here, I'm going to go ahead and simplify whatever I can. Now we need to be really careful because this 5 to the negative 2, all right, is really going to be 5 to the positive 2 because I can flip it, the reciprocal rule. All right? Now the next thing, and let me use a highlighter here so you can see exactly what I'm talking about. So we have s to the negative 4 and s to the second. So directly underneath, I'm just going to write what I'm doing. So s to the negative 4 minus 2, okay? So that's going to be s to the negative 6, all right? I'll worry about simplifying completely at the very end. Finally, and this is the tricky one. You really, really, really want to be careful. We have t to the 8th and then t to the negative 2. And like I said, we need to be really, really careful because this is going to be t to the 8 minus parenthesis negative 2, which really makes this t to the 8 plus 2. And that's going to be t to the 10th. So you want to make sure that if you're not getting these like instantly, and that's fine, you got to slow yourself down and make sure you just walk yourself through these rules. So finally, let's go ahead and simplify completely. 5 to the second is 25. This s to the 6 or negative 6 is going to be s to the 6th and then t to the 10th in the numerator. All right? Now, the next set of rules that I'm going to be looking at, all right, are going to be, they deal with radicals. Now, the one thing we have to remember is that the basic definition of a radical is if you have the square root or the mth root of a to the n, then we can rewrite this as a to the n over m. In other words, it's a fractional exponent. That's what radicals are. They're fractional exponents, okay? So if we wanted to, we can go ahead and look at a couple examples of simplifying them real quickly. So if we look at the square root of 25, we know that equals 5, okay? But very few people actually understand why it actually equals 5. It's kind of like one of those things like you just like memorized it. In fact, there is like a really, really nice rule, and it says if a to the second equals b, then the square root of b equals a. Okay? So if I come directly underneath and kind of just substitute my information here, if 5 to the second equals 25, then the square root of 25 equals 5. Okay? And notice how the letter A's match up in my definition, and then the letter B's match up in my definition as well. But like I said, very few people really fully understand what's happening here. So in reality, here's what's happening. The square root of 25, I can rewrite that as the square root of 5 to the second power. Now, if I apply this definition up here, then I can rewrite that radical as 5 to the second, all right, all raised to the 1/2 power. Because remember, the m is going to be the denominator. The m is called the index. And then you have the variable. Which is the letter n, which is our exponent for the numerator. So in reality, you really have that situation right there, where 5 to the second, okay, 5 to the second is raised to the first power. Now, I know this is kind of going really in depth here, but now you can see that we have 5 to the second raised to the 1/2 power, which is a power rule. It all goes back to the rules of exponents. So when you have a power raised to a power, you multiply the powers together, you get 2 over 2, which is really 5 to the first power, or just the number 5. That will help us later on, okay? So if you've never seen that before, make sure you just go ahead and rewind the video and check it out. If you have any questions with it, feel free to email me about it. But we're going to keep moving here. So let's look at another example here where we can simplify something real quick. Let's look at the 4th root of 16 x to the 8th. So when we simplify this, we're going to get 2x to the second. Now, there's a really, really easy way to do this, okay? Especially with the variables. Numbers are a little bit different because you got to know some stuff. For example, with numbers, you definitely want to know your squares. Okay? You definitely want to know these. For your cubes, you definitely want to know, and I'm going to write out the ones that we should know. All right? So let's see. 1 to the third is 1, 2 to the third is 8, 3 to the third is 27, 4 to the third, 64. 5 to the third is 125. Those you should know. The fourths, you really don't have to know too many, but you should know a couple of them. So 1 to the 4th is 1. 2 to the 4th, 16. 3 to the 4th is 81. 4 to the 4th is 256, and so forth. Okay, these are like basic ones that we should know. So here's what I did real quick, all right? I looked at this situation here, the 4th root of 16x to the 8th as this. I looked at it as 2 to the 4th multiplied by x to the 8th. Now, the 2 to the 4th, if you look on the far right side of your screen, highlighted in green, that's this situation right here. So I know the 4th root of 16 is going to be 2. Like that one is pretty straightforward. And once you see what I'm really doing here, you can apply it. The exponent, all I do to figure out what the exponent is real quickly is I take the index, and I take the exponent on the inside, and underneath, I just divide the two. I figure out how many times does 4 go into 8. In this case, it's going to be 2. Using just long division. So this 2 right here tells me my exponent outside the radical, and the 0 tells me the exponent inside the radical. All right? So outside, inside. So that's how I got 2x squared really quickly. Let me show you another scenario here where we actually get like remainders and stuff like that. I want to show you how I'm going to write that. So here's a situation here where we have, let's say, we'll keep it simple. The square root of 121, x to the 10th, y to the 3rd, and z to the 9th. Okay? So here, my index is a 2. Now what's really nice, the number's really easy. So the square root of 121 is going to be 11. But now I have to worry about all the variables. So if you look, and I'll do the x first, I just divide 2 into 10, so that gives me 5 with a remainder of 0. So this is going to be x to the 5th. Now for the variable y, 2 divided into 3 goes once with a remainder of 1. So I have y to the 1st, and then I have a y to the 1st left over on the inside. And then z is going to be 2 divided into 9 goes 4 times with a remainder of 1. So it would be z to the 4th and z to the 1st. And that is how fast you can simplify very complicated radicals. All right. Now we're going to transition into simplifying radicals using expressions. So for example, the square root of 5 plus 3 square roots of 5 is 4 square root of 5. And we can do that because technically there's a 1 out in front of the first square root of 5. And then the radicals themselves match. So it's just like combining like terms. The hard part becomes, what if they don't match? Like, how do you do that? So here's an easy example here. So we're going to do the square root of 75 plus the square root of 48. So currently on the surface right now, it looks as if these two radicals do not combine. However, we need to simplify them first to break them down into something that maybe that might be a little bit more manageable. Now, earlier I mentioned that you definitely want to know these perfect squares, perfect cubes, and perfect fourths on this table here. You definitely want to know them. But if you notice, square root of 75 or the square root of 48, nowhere near on this table. So the easiest way to do that, okay, is to go ahead and break these down into numbers that you know. For example, 75 is really just 3 times 25. Now, if you notice, 25 is one of those numbers on my table. So what I'm going to do is I'm going to rewrite 75 as 25 times 3 plus. Now the 48. Now 48, I'm going to break this one down all the way. And let's see if you remember what I'm doing here. Okay, I'll tell you what I'm doing after I'm done. But I want to see if you can remember what technique I'm actually using here. So 4 times 48 is really 4 times 12. Now the 4 can be broken down even further to 2 times 2. The 12 can be broken down into 4 times 3. And then this 4 can be broken down into 2 times 2. So notice I have nothing but prime numbers left over. This is called prime factorization. Okay? And what makes this so powerful is the fact that we know when we group 2 times 2, it equals 4. So I know underneath the radical here, I have a 4. I have one 4. Then I have another 4. And then finally, I have a 3 left over. Okay? So I can use prime factorization to my advantage to quickly simplify a number so that I can simplify radicals real fast. Now, in red, there's another property that we learned a long time ago. And it deals with this. It says, if you have the multiplication of more than one, I guess, term or thing underneath the radical, like a times b, then you're allowed to break them up. So that's exactly what I'm going to do with my problem. So I'm going to break up the first term into the square root of 25 times the square root of 3. And then I'm going to break up the second term as the square root of 4 times the square root of 4 times the square root of 3. And if you notice, when I have those perfect squares, like 25 and then the 4 and the 4, I put them out front because I know I'm going to simplify them later. So finally, we can come straight down. We get 5 square root of 3 plus 2 times the square root of 3, which is really 5 square root of 3 times 4 square root of 3. And then we can add them to give you 9 square root of 3. So yes, I definitely really drug this problem out in terms of like time, but I really want you to see how the little things that we learned a long time ago make massive impacts in the things that we do later on in mathematics. And that will be a common theme throughout the entire course. We're getting to that point now where those little basic techniques, we got to be able to apply them real quickly because it's going to help us later on to simplify more complicated problems. Another thing is we're transitioning from being very good at computational mathematics, okay, like computing stuff, and we're going to be turning into more analytical mathematics, being able to look at a situation, use some math to describe what's happening, especially when we start talking about higher order polynomials and finding roots or zeros, if you will, to the polynomial. All right, so that's going to be basically it for this review. Okay, if you have any other questions, all you got to do is just email me, and I'll see you in the next part. See ya.